right, welcome to Chapter 7. Chapter 7 is about differential equations and mathematical modeling. And we're going to start by, first off, defining differential equations and talking a little bit about them. And then we're going to work into something called slope fields, and we'll get into what that is. But just so you know where we're going, let's start with a quick definition. And the definition here is a differential equation. A differential equation is an equation involving a derivative. Now, this comes from Chapter 6. You may remember that we said if we've got y equals x squared, dy dx is equal to 2x. That's a derivative of y with respect to x. And the differential equation dy is equal to 2x dx. And I would encourage you to go back and watch my Chapter 6 videos if you're not sure of the significance of that. So that's just something we need to know. When the words pop up, now you know what that means. So let's take a look at example 1. And example 1 is solving a differential equation. Solving a differential equation. By the way, often abbreviated DiffEq. At college, you will take DiffEq, differential equations. Tons of fun. So we start with dy dx equals secant squared x plus 2x plus 5. And the goal is to find all equations y equals that satisfy that derivative. So looking at this, what we know is that the solution is any antiderivative. And you spent a lot of time in the last chapter working with antiderivatives. So let's see what we know. Well, first off, we know that the derivative of tangent is secant squared. So tangent is the antiderivative of secant squared. We know that the derivative of x squared is 2x, so x squared is the antiderivative of 2x. We know that the derivative of 5x is 5, so the antiderivative of 5 is 5x. We also know, excuse me, that the derivative of a constant is equal to 0, which means that theoretically, there could be a plus 0 on the end of this derivative, which means that we need to put a constant on the end of this function. Notice that this antiderivative, this function that has a derivative of secant squared plus 2x plus 5, has to have a constant on the end, because there are going to be, and we'll see this a little bit later, there's an infinite number of possible functions that would have that derivative. We'll go into more details about that later, but always plus c when finding an antiderivative. All right. Unique solutions. Here's the problem with unique solutions. If this is a function, notice that each of these functions will have the same derivative. If you want to find the value of c, what you have to do is you have to be given some point on the graph, which then says, aha, it has to be the one that goes through that point. We will come back and talk about that later. And in the meantime, my students go ahead and do exercise 1 out of the textbook, and we'll come back with example 2. All right, welcome back. Example 2. we are going to be given that initial value. I told you that if you had a point on the graph, you could figure out which of those infinite graphs went through that point. So the initial value problem is here is a point on the graph. So the derivative with respect to x of this function is e to the x minus 6x squared. And we are told it goes through the point 1, comma 0. So whatever it looks like, it goes through that point right there. Now, let's see what we got. Y equals, well, we know that the derivative of e to the x is e to the x. Therefore, the antiderivative of e to the x is e to the x. We know that the derivative of x cubed is x squared. But of course, the derivative of x cubed is 3x squared, and we've got a 6x squared, so we're going to need to put a minus 2 in front of our x cubed. And it's just a good habit to be in to just very quickly take the derivative in your head to make sure you got the right one. Pull down the 3, that's a 6. Reduce that by 1, that's a 2. Good, I've got the correct original function. Plus a constant, always plus a constant. Now, because this goes through the point 1, comma 0, I can substitute. And what I see is that I've got e minus 2 plus c, which means that my constant is 2 minus e, which means that whatever this function looks like, I have absolutely no idea, but it goes through that point right there. And all of the other derivatives or functions that have the same derivative, notice same slope at every single point on every single one of these functions, but only one of them goes through the point 1, comma 0, which means that my function has to be y equals e to the x minus 2x cubed plus 2 minus e. And this is called a particular solution, whereas the last one was called a general solution. All right, my students, go ahead and do example 13. I'm trying to make these videos short, so we're going to stop right here and we'll come back with a couple more examples in video 2. Thanks for watching. Hope you learned something.